There we go. So yeah, for the fuels, like I was saying, this chart here, the compression curve, you need to have enough pressure in the cylinder because that goes hand in hand with what? Well, the temperature, right? Which is important for ignition, yeah. So if you have insufficient pressure in the cylinder, then the air temperature is not going to get high enough. Insufficient air temperature, when you spray the fuel into the cylinder, it's not going to ignite, okay? So the compression, let's just start with that in the cylinder. What are a couple of factors that could affect the compression? Okay. So how well we're actually sealing the cylinder, that's what you're getting at. So piston rings, head gasket, valves actually sealing, all of that, yes, absolutely. What else? Okay. How much air are we actually getting into the cylinder? So do we have a turbocharger? Do we have maybe a plugged air filter? Right? So if you don't get enough air in, it's kind of hard to have enough to compress to get the temperature. Okay. Is there anything else that could affect how much pressure we're able to build? So in sealing, I heard something. What was that? Okay. So what's the air temperature that we're sucking in? So not only how much air we have in there and how well we're sealing it, but also what was the temperature we started with, because we're trying to hit a target temperature at the end of compression that's high enough for the fuel to spontaneously combust. Okay. Providing that I have sufficient air in the cylinder and sufficient temperature for combustion to happen, when I start injecting fuel, right here we have the beginning of injection shown. When I start injecting fuel, there's going to be a little bit of lag between when I inject the fuel and when it actually starts to burn. Okay, so we do have this spot over here, and this is number 1. We have a name for that. Do you guys remember what that was? That'll be your ignition delay. Okay. Now, I heard injection lag, and that's actually something that's on older, we had pump line nozzle type systems we had to think about. Okay. Injection lag would have been the period of time between when I first started to pressurize the fuel to when it actually started to get injected. Okay. So if I had an old school, mechanical fuel injection pump and some hydromechanical nozzles, what I'd do with the fuel injection pump is I would start building pressure in the fuel line. As soon as I start building pressure in the fuel line, well, that doesn't mean that injection is actually taking place yet. We have to get to the nozzle opening pressure on the injector before injection starts. So that's what would have happened over here. Okay, that would have been the injection lag. And there's a couple of factors that may affect injection lag, and one of them absolutely is what the nozzle opening pressure is, because if you have difference in nozzle opening pressure between injectors, that's going to affect how long that injection lag lasts cylinder to cylinder. There's another factor that will affect injection lag. What is that? Line length. Because the longer line is going to have more fuel in that line to compress and get up to injection pressure. So quite often what you'll find is your injection lines are coiled for the cylinders that are closer to the injector pump, and they make more of a straight run over to the ones that are further away. If you take all those lines and straighten them all out, you'd find they're all the same length. So back to ignition delay. Ignition delay is the difference between when we start spraying fuel in the cylinder and when that fuel starts to burn. Okay. So factors that can affect ignition delay. What would that be? Okay, so temperature. So in-cylinder temp, ambient temp, engine temp, all of that stuff, yes. How well did we atomize the fuel? So the fuel itself, the cetane rating of the fuel, we'll get to that in a second here, a little bit more detail, but off the top of your head, what do you think the cetane rating of the fuel actually means, or what is it referring to? So we always say the definition of a cetane rating is the ease of self-combustion, but the reality is that means what's the auto-ignition temperature of that fuel? At what temperature will that fuel spontaneously combust? Okay. Is there anything else?
Type injectors.
Okay. So the type, I think atomization would probably tie into that. What type of injector you have? Okay. Timing plays a big role. Okay. When it comes to timing, if I start to inject the fuel sooner or later, take a look at the combustion curve and understand that the combustion curve is tied to the temperature in the cylinder, right? So if I try to inject the fuel sooner, that means I might not be quite as far up temperature-wise in the cylinder. Or if I inject it later, I'm further up temperature-wise in the cylinder. So let's say I have a cold engine. Is it going to start easier with early or late timing? Late timing, because there's already more temperature in the cylinder when I inject that fuel. Yeah. Number two, if you take a look at our chart here, you can see that the fuel has started to burn, and there's a rapid rise in pressure and also temperature in the cylinder. So number two, what do we call that? We're not at peak pressure yet, because that happens at the end of number three. Yeah. Uncontrolled combustion, yeah. Okay. So this here, uncontrolled or pre-mixed. Okay. So we inject a bunch of fuel starting at the beginning of number one all the way to the end of number one, but we didn't actually burn it yet. So that means there's a bunch of fuel in the cylinder that hasn't burnt yet. During period number two, we're continuing to inject fuel, and we're also, we're burning the fuel that was already in there. Okay, so there's going to be a rapid rise in pressure and temperature, and then at the end of number two and continuing, on through number three, this is going to be controlled combustion. Yep, there we go. Controlled combustion. We want the premixed combustion to be as short as possible and the controlled combustion to be as long as possible. And the reason we care about that nowadays is because we're trying to minimize emissions and maximize power output. Okay. So is there some stuff we could do on a modern engine with electronic fuel injection control that would help us to tailor this? You want number two to be as short as possible and number three to be as long as possible. Okay. So what we could do is pilot injection. That will minimize the premixed combustion. Okay. And then for controlled combustion, what we might do, if we want to take total control of what that pressure curve looks like, is multiple injection events. Okay. Number four, this happens after we stop injecting fuel. If you take, go ahead. That's afterburn. That's what that's called. Yeah. So that afterburn period, that's where we finish burning the fuel that was injected. We want to make sure that this afterburn period doesn't extend too late in the power stroke. If the afterburn period extends too late into the power stroke, that means that the risk of there being unburned fuel leaving through the exhaust valve, it goes up. If the afterburn period extends too far, if we didn't have enough time or air in the cylinder to finish burning the fuel that was in there, usually we're going to see that as particulate matter, black smoke. Okay. So when we're looking at this chart here, there's another thing that we can see. We're going to look at the combustion curve here for this. Or not the combustion, the compression. Apologies. So we come up. Now you do understand that to compress the air in the cylinder, it takes energy, right? So when that piston moves up, it does take energy to compress the air. And if I don't inject any fuel, that means that the pressure in the cylinder is also going to help to push the piston back down, right? And when it pushes that piston back down, I mean, you spend energy compressing the air, you get it back, helping the piston come back down. But what if we didn't let that air pressure help the piston come back down? What if we just dumped that pressure out at the end of the compression stroke? That would mean we'd expend energy compressing the air, but we wouldn't get any return on the way back down, right? Okay, what system on the engine does this? Your jake brakes, your compression brakes, right? So an engine compression brake or a jake brake, it allows the engine to spend energy compressing air, and then at the end of the compression stroke, we open up the exhaust valve momentarily and we vent that pressure into the exhaust system. And that's how you get that engine braking effect. If you don't have any type of engine brakes active on the engine, you get a lot less engine braking on a diesel engine, a lot less. Okay. One of the things we referenced was the fuel. And the fuel that we use in an engine, we typically assign it an octane or a cetane rating, right? But what does an octane or cetane rating actually mean? Where did those numbers come from? Well, when you take hydrocarbons, okay, what you're talking about is a mixture of carbon and hydrogen. Okay, so this is a hydrocarbon chain right here. If I take that hydrocarbon chain and where did that go? Hold on a second here, guys. So I'm going to copy that. So I'm going to take that hydrocarbon chain, I'm going to put it over here, but I'm going to make it longer. There's more of it. Right? So you can see for the cetane versus the octane rated fuels, it's a longer hydrocarbon chain. Okay? We say that cetane rated fuels, we rate them by their ease of combustion. What that really means is we rate them by how easy or how low their auto ignition temperature is. Hydrocarbons with a shorter chain towards the higher end of the octane rating number, those ones we rate them on their resistance to self-combustion, okay, or how high their auto ignition temperature is. The reason that a longer hydrocarbon chain is easier to start on fire at a lower temperature is because there's more of these bonds to break. Okay, anywhere you're going to start snipping apart that hydrocarbon chain, if you got more opportunities to do it, it's going to happen easier. Or another way to interpret that is at a lower temperature. Looking at this, a longer hydrocarbon chain, the longest one that we would use would be something called pure cetane, because cetane is a specific length of hydrocarbon chain or a specific type of hydrocarbon. We have something in the middle over here where it is kind of the 0 point between how cetane burns and how octane burns. Does anybody remember what that's called? Okay, so heptane, that's in the middle. Pure cetane, that would be 100 cetane or 100% cetane. The 0 point would be pure heptane, and then on the other end of the spectrum would be pure octane. Now, we don't bother trying to refine fuels to the point where you have pure cetane or pure octane. We don't care about that. What we do care about is that a fuel that has, a 90 or 87 octane rating, for instance, for normal pump gas, it burns like a mixture of 87% octane and the remainder of heptane. Okay? The same with a cetane rated fuel. We care that most diesel fuel burns as if it were a mixture of somewhere between 40 and 50% pure cetane, the remainder of heptane. That's how we come up with these ratings. Okay? The shorter the hydrocarbon chain, the harder it is to start the fire. Okay? The longer it is, the easier it is to start the fire. And when we're talking about a fire happening in the cylinder, that combustion science that you guys would have talked about in your level 3 fuels, you would have been talking about that triangle, right? Where you have to have heat, you have to have fuel, and what was the other thing that mattered? Oxygen. Because what we're trying to do with these hydrocarbon chains is burn the fuel or oxidize that fuel and turn it into carbon dioxide and water. So any questions on the combustion science part of this? Pretty straightforward. Okay, let's move on. Do you remember looking at a couple of diagrams like this? So these diagrams, these are showing you a simple example of a mechanical governor. A very simple example. When we're talking about a governor, a mechanical governor, there's a couple of major components. You have your flyweights and you have your spring, right? Your governor spring. In modern engines, we don't use these anymore, but we still control an engine based on the same principles that this mechanical governor uses. All right? So a few things to consider here, and we're just going to look at this one first. This governor here has a throttle, and what does that throttle do? It lets us change the force on the spring. All right, we have some flyweights. That's going to be these guys right here. What do those do? Well, when the engine's running, they're spinning. The faster they spin, the heavier they are, and the more they're going to want to swing out, right? Counteracting the centrifugal force of those flyweights is going to be the spring. So the spring, that's the thing that the operator controls. The flyweights, that's kind of the engine's input into the system. There's going to be typically some hard limits to how far that throttle moves. And that's going to change the minimum and maximum force that I can develop with the spring. Okay. So looking at these two things here, the top one, is that the minimum or the maximum force? The top one's going to be the max, and the minimum is going to be the bottom one. So this here is my low idle adjustment and my high idle adjustment. Okay. The high idle adjustments, maximum spring force, that means the engine has to spin the fastest it's going to develop enough force on the flyweights to counteract that. And when it does that, it's going to pull the fuel rack up. Fuel rack moving up, that's less fuel. Fuel rack down, more fuel. Okay? So what's going to happen here is as this engine is running, the engine RPM is going to start going up. Okay? And if the engine RPM ends up getting fast enough, the flyweights will swing out, they'll balance out against that spring force, and it'll limit how much fuel is getting injected. Okay. As I move that rack, I'm also changing how far, I shouldn't say how far, but the fuel position of whatever metering system I have inside that fuel pump. Okay. Now, sometimes I don't actually want maximum fuel injected. Sometimes I do want maximum fuel injected. But what controls maximum fuel? And it's actually not the spring force, because if the flyweights are heavy enough because the engine is running fast enough, we're going to compress that spring, right? If the engine RPM starts getting dragged down because of load and we start adding more and more fuel and we get that engine to carry the maximum load that it can, eventually we're going to stop rack travel with a screw. Okay, and this is very, very basic the way I'm drawing it here. But imagine there was a screw that could limit how far the rack could travel. This would be our horsepower screw, so to speak. Okay? Or your maximum rack travel limit screw. Sometimes we don't want to get to the maximum fuel position immediately. What if we had an engine that had a turbocharger? Would it make sense to go straight to full fuel if you don't have a cylinder that's completely full of air yet? No. And if you do, what happens? If you put in more fuel and you don't have enough air to actually burn that fuel, what happens?
Black smoke.
You get lots of black smoke. Okay, so rather than have a huge puff of black smoke when you hit the throttle of max fuel and you don't have that turbo spooled up yet, what do we do?
Use an anaerobe.
Aneroid. So an aneroid is basically a little blocking mechanism, and it will limit the maximum rack travel. Until you have boost. So you're going to have what's effectively a little piston. Often this aneroid, that's what this thing is. So often that aneroid is just a diaphragm and then some sort of a linkage that's going to block the fuel injector pump from going to full fuel until you get that boost. Okay. But yes, your aneroid, it's going to limit maximum fuel right up until we get boost present. And then once you get your full boost, it moves up out of the way, lets you get all the way over to the horsepower screw. Okay.
This is like a diaphragm, right?
The aneroid is typically just a diaphragm, yes. A lot of what we looked at here, we still do on electronically controlled engines. We do exactly what we're showing here, but we just do it with some sensors and some programming, right? Okay. So high idle, low idle, those are going to be values that are programmed into your ECM. Okay. The flyweights, what is the equivalent to flyweights on a modern engine? If the flyweights are a way to signal a mechanical governor what the engine's RPM is, what's the equivalent to that on an electronic engine?
Speed.
Your crank speed sensor. Okay. The equivalent to the throttle lever. It's going to be your throttle position sensor on a modern engine. It's just a sensor, right? The aneroid, what's the equivalent to an aneroid on a modern engine? Your boost pressure sensor. Okay. Your horsepower screw, that's just the value that's programmed into the controller. Okay. We can change that. Another thing that's interesting, if you look at these two examples here, is one shows a single spring and one shows two springs, a very light spring and a big heavy spring. Okay. So on the left-hand side, we have a spring that we can change the effective, let's consider just the weight of the spring. Okay. And let's say, for instance, if I was to put 5 pounds of force on that spring, that would equal low idle. Right? If I move that throttle lever and put more force on the spring, that might bring me up to high idle, 2200 RPM, right? And if the engine has enough load on it, the engine load is going to slow down the engine to the point where those flyweights aren't as heavy. They don't weigh 22 pounds anymore. So now they start to collapse. And now that rack starts to move towards a more fuel position. Okay. As I drag that engine RPM down, and as that rack, as those flyweights collapse, the rack is going to move to its maximum fuel position, which might be, 18 pounds, which would be 1800 RPM, which is where that rack is fully collapsed. Okay. If I put the most fuel into an engine, that means I'm putting the most pressure in the cylinder. That means I'm making the most torque at a certain RPM. Torque times RPM divided by 5252. What is that formula telling us? That was engine horsepower, right? So to get maximum horsepower, I actually have to slow an engine down. When we get to this chart here, we'll talk about that specifically. But that drop in RPM from high idle to rated speed, which is where the max horsepower happens, we call that our speed droop. Okay. On a mechanical governor, it's necessary for that to happen. That has to happen so that we can get the rack to move over. On an electronic engine, it's not nearly as critical. There's still going to be a little bit of droop. but it doesn't have to be that drastic. Looking over at this other example here, this one has a very small spring. And let's say this little tiny spring here, come on. Let's say this one was a 5-pound spring. That means if I'm completely off the throttle, that little 5-pound spring is the only thing balancing against the flyweights. That gives us low idle. If I go ahead and apply the throttle a bit, I'm going to collapse that 5-pound spring, and now I'm pushing on a heavier spring, and that spring takes 22 pounds for it to collapse. So that means if that big spring is 22 pounds and the little spring is 5, I collapse the 5, and then I've more or less got a solid link between the throttle lever and the fuel rack. Any changes in position I make to the throttle lever are going to directly affect the fuel position of that plunger. This is going to give me direct control over how much fuel goes into the engine with my foot, for instance. Okay, so this governor here, it's only going to limit fuel injection with the governor at low idle and at high idle, and anything else in between is up to me and whatever I'm doing with my foot. Okay, these two governors, two different styles of governor. One is a variable speed and one is a limiting speed. Okay, this is something you're going to want to know. This one here is a variable speed, and this is a limiting speed. Limiting speed is kind of a min-max governor. It limits low idle and high idle. That's it. Why the difference? Well, one is what we would call an on-road governor, and one we would call an off-road governor. Which is which? The on-road would be your limiting speed. Years and years ago, when they were developing governors for diesel engines that were used in highway trucks, they wanted to have ones where if the operator or the driver would blip the throttle with their foot, they could directly affect engine RPM, which made it easier to shift gears, right? If you have a variable speed governor, this one, it's very, very good for holding a specific engine RPM even as the load changes. This is great for stuff like farm tractors and bulldozers and heavy equipment, right? If you have a change in load because the work that you're doing with the machine changes, but you still want that engine to run at the same speed, a variable speed governor is much more desirable. Nowadays, when it comes to electronic engines, you can have an engine react whichever way you want it to. Historically, you could have had two, Cummins 855 engines. One was in an old Western Star truck, and one was in an old versatile farm tractor, right? The injector pump was different on those two engines because one was supposed to work like a truck engine and one was supposed to work like a tractor engine, okay? Nowadays, it's just a couple lines of programming, and often both of them exist on the same engine. Get into a modern semi-truck, flip on your PTO, and guess what? It starts acting like a variable speed. Turn on your cruise control, guess what? It acts like a variable speed, okay? Turn your cruiser PTO off, now it's a limiting speed, and you're controlling engine RPM directly with the throttle position sensor, okay? So nowadays, the difference between these two is just the mode that the engine's trying to operate in. Historically, it was literally two different injector pumps that had different types of governors inside of them. This diagram here. This one is just an example of the horsepower and torque curves that you would have in a typical diesel engine. These numbers and the way these curves show up, they're going to vary from engine to engine. This would be based on governor design. It might be based on how the ECM fuel mapping is programmed. With the governor, these values here, they had to do with basically what your governor spring was set to do, what your horsepower screw was set to do, and how much fuel it could actually pump when that plunger was at the maximum fuel position. That would affect that horsepower and torque chart. Okay. But over here, on this chart, we're going to identify a couple different points. So first of all, we have our minimum engine operating RPM, number 1. Okay. We have the maximum engine RPM, number 2. We have a point over here. We'll pull that one down. That is where we make the most horsepower. Number 3. We have another point over here. This is where we make the most torque. That's number 4. We have the difference between 3 and 4 there. This is between peak torque and peak horsepower. We call this the operating range of an engine. Between number 3 and number 2. Remember I said that when you apply load to an engine, the RPM is going to drop off a little bit until we get to full fuel. Okay, this we call speed droop. And we'll go ahead and we'll make a list of these in just a moment. Okay, well, yeah, speed droop. Okay. Number 3, the RPM that happened at, we call rated speed. That's where peak horsepower happens. And your peak torque speed, number 4. The difference between these two we call that torque rise. Okay. So torque rise, again, this is just a characteristic that's either mechanically built into a governor or electronically programmed into the fuel map on an engine controller, right? But that torque rise, this can be very handy because as you lug that engine down, you don't want the torque to just fall on its face because it's going to feel like kind of a gutless engine. So you want that thing to pull harder as the RPM drops off to a certain point. Okay. So number 1, low idle. Number 2, high idle. Number 3 is the rated speed, and that's where peak horsepower happens, by the way, right? Number 4, that's your torque. Peak speed. When you hit that torque peak, that's going to be at a lower RPM than when you hit your rated speed or your maximum horsepower typically. Okay. Number 5 is the operating range. Number 6 is the speed droop, and that's where that engine RPM drops off as we get to full fuel from high idle. And number 7 is the torque rise. And torque rise is usually expressed in foot-pounds of torque. Okay, or I suppose if you're European, it'd be Newton meters. Okay. So when it comes to this governor terminology, this is something that you will want to be familiar with. For low and high idle, those are either adjusted mechanically with a screw that limits the minimum and maximum physical throttle position, a simple screw adjustment. Okay, the rated speed, which I guess we should go ahead and put your peak horsepower, that's where that happens. This is going to be adjusted either with a couple of lines of code in a controller or maybe a physical adjustment that limits how far the rack can travel, your horsepower screw. Okay. Torque peak speed, again, just a programming point on the fuel map or a physical adjustment of maybe a torque capsule. I think that's what they used to call it on those old Bosch pumps. Okay. The operating range, this is just a characteristic of the engine itself and the way that the fuel pump or the programming is designed. The speed droop, this is one that we should talk about a little bit, okay? For a lot of engines, the speed droop is just a factor that we don't really think about because, for the most part, it doesn't matter unless we're talking about one specific application where having a zero droop governor is ideal. A zero droop governor or an isochronous governor, I don't know if you guys remember that term. That has to do with a generator governor, yeah. Because you want that engine to run at the same RPM even as the load changes. You don't want it to start off, up at 2200 and then drag itself down to that 1900 RPM. I think that's about what this is showing us here, right? What you'd want is you'd want that engine running at, let's say, 1800 RPM, regardless if there's no load or full load. It always stays at 1800 RPM to give us our 60 cycles or 60 hertz out of the genset that's attached to it. Okay, so a zero droop governor as a generator governor is pretty necessary. Right? What do you think would happen if the governor spring, that's this right here, if that governor spring broke? Would the engine run away or would it just die? Right, well, two options again here. So the spring is the thing that wants to push it to a more fuel position, and the flyweights want to take it to a less fuel position. So if there's no more spring force, it's going to die because it's going to immediately go to a no fuel position. Yeah. So I guess after talking about the different types of governors that we have, we should talk about what they're controlling. For fuel injection systems, you're going to have different ways to meter the amount of fuel that gets injected. Okay, there's distributor style pumps that may have maybe inlet metering. A distributor pump, by the way, is a type of pump that has one high pressure pumping element or system. A multi-plunger inline type pump is going to have an individual high pressure pumping element for each cylinder. Okay, when we get into electronic fuel systems, if you have electronic unit injectors, you have an individual high pressure pumping element built into each unit injector. If you have a high pressure common rail, you have a high pressure pump, and then you have individual injectors that can open and allow that pressure into the cylinder. So different fuel metering systems. One thing specifically that I want to talk about for this inlet metered system here, or any distributor pump for that matter, is when I look at the pump, down at the bottom, I can see I have, it looks kind of like a screw hanging out the side, but inside, behind that screw, there is a little hydraulic piston, okay? That piston there, fuel supply pressure that's going to the pump itself is going to act on that piston, and it can push that piston over. Let's see if I have this picture will work here. So when that piston is moving, what it's doing is it's actually rotating the cam ring just slightly one way or the other. Okay, this cam ring here, it has these lobes, as you can see, that the rollers are going to ride up, and they're going to push these plungers together. These plungers, they sit inside of what we call the rotor. Okay, and as they push together, they're going to pressurize any fuel trapped between them and force it out to a delivery passage in the hydraulic head. All right, so if I was to take and rotate that cam ring a little bit, what I do is I change when those plungers started getting pushed together, because I'll change when they hit those ramps. Okay, what do you think I'm trying to do by moving that cam ring? That's my timing advance. Yeah. So a distributor pump, whether it's an old school mechanical one or whether it's a newer electronic distributor pump, which we still do use on smaller engines nowadays, it's going to have typically some way to advance the position of those fuel ramps by rotating that cam ring with a little hydraulic mechanism. when we're talking about a multi-plunger inline pump, we're going to have a fuel rack, and it's going to rotate the position of a plunger inside of its bore, like so. And when that happens, it's going to change the position of this port and helix metering system to give us more or less fuel. Okay. We're looking at a system like this, and again, for the IP, if they ask you any questions about mechanical fuel injection systems, it's likely going to be on a multi-plunger inline type system. Okay. Right now, you have to imagine the plunger, and that's this part right here. Okay. That's the plunger. When that plunger is all the way down at the bottom, that's the lowest position on the camshaft. Okay. And this right here, this is where we fill the barrel. Okay. So I have that area in orange. That's my fuel galley, and you can see the arrows there pointing between the fuel galley and the barrel. Down at this position, we're just filling, and we're getting ready for an injection event. As we start to get closer to wanting to inject fuel, we're going to start lifting that plunger up with the camshaft underneath it. I'm going to get to port closure. Okay. So from the bottom dead center up to port closure, nothing's really happening yet. But once I get to port closure, now the fuel is trapped. And you can see this area over here in red. That trapped fuel is going to start building pressure. So this right here, port closing, this is where injection starts. Right, beginning of injection. The beginning of injection is going to last all the way through this pumping phase. Okay, right up until the bottom edge of the helix, right here, clears the port. And then I'm going to have a leak path between whatever trapped pressurized fuel was up in the barrel and the fuel galley in the body of the injector pump. Port opening, this is the end of injection. Okay, now I've lifted that plunger high enough, the bottom edge of the helix has cleared the port, and now fuel can leak out into the port. This is the end of injection.
That's your fuel pump spill?
Yep, this right here is the spill part. Fill, pump, spill, yes. If I don't want to inject any fuel at all, what I'll do is I'll rotate the plunger around, and if we move up a slide here, you can see we had that, it looks like a keyway cut into the side of the plunger. If I line that up with the port, I can move that plunger up and down all day. It's never going to build any pressure. This is zero delivery. I'm going to do this for one of two reasons. Either I want to shut the engine off, or what's the other one? Decelerating fuel cutoff, right? So basically, decelerating fuel cutoff means I'm not requesting fuel, my foot's off the throttle, and we have the inertia of the drive line pushing the engine. Flyweights will swing out to a no fuel position, and here we are. Okay. Partial delivery or maximum delivery. This is dependent on rack position, and we're either going to expose a very small portion of the helix here. Maybe this pen will work better. A very small portion of the helix, or perhaps a larger portion of the helix to the port. If I use the longer part of the helix, that means the port stays closed longer. That means there's more fuel getting injected. And this right here, this is where we'd be for peak horsepower. Okay. Over here, the smallest part of the helix is covering the port, and that means fuel delivery lasts for a very short period of time. Minimal fuel delivery, this will be low idle, high idle, any low load engine situation. This is where we're going to be over on this side. Okay. So you may have noticed up at the top, we have the spring and this poppet looking thing up top. This is called the delivery valve. It has a couple of purposes. One purpose is to maintain a little bit of residual pressure in the line. This helps to minimize injection lag. And the other thing, it is also called sometimes a retraction valve. So it acts kind of like a piston. When the pressure goes down in the plunger, because we're at the end of injection, as we're showing here, that delivery valve is going to drop. And think of it almost like a plunger, maybe from a syringe or something like that, sucking fuel back out of the injector line. Okay? And the reason we do that is to drop the injector line pressure very, very quickly and get it well below the nozzle opening pressure, so we have abrupt end of injection. You don't want that injection pressure to kind of bleed down slowly. You want it to end quickly. Okay.
Is that called shattering?
So the chattering doesn't happen here. It happens in the injector nozzle itself, and that happens
directly affected, right?
Yeah. We don't want that thing to kind of slowly bleed down. We don't want it, chattering on its way down. You just want it to stop. It injects and it stops. Yeah. Okay. So in terms of chattering, chattering is actually one of the things that we're watching for when we're testing our nozzles. And the type of nozzle we'd be testing would be like a mechanical or a hydromechanical fuel injector nozzle, an electro-hydraulic injector nozzle, the style that you'd see on a high-pressure common rail engine. We don't test them the same way. Okay? But a hydromechanical nozzle with a pop tester, that's probably what you're familiar with from previous training, right? So the type of injector nozzle that you'd be checking there is going to have a spring. I'll see if I can find a better picture. This one's pretty good. So go ahead and drop this in here so we can zoom nicely. Okay. So a hydromechanical nozzle is going to have probably two connections to it. Usually there's two connections. One is where the fuel injector line goes, and the other one is going to be a return line. Okay. Your fuel injector line, we'll go ahead and highlight that here. It's going to let fuel come in, and it's going to feed it down towards the bottom of that injector nozzle. At the bottom of the injector nozzle, we have a needle and a seat. The needle and the seat. Okay. A spring keeps that needle held tightly against the seat, and fuel pressure has to build. And there's a little shoulder on the needle right here, and the fuel pressure has to build and act on that shoulder to lift it up against the force of the spring. Okay, so how much pressure does it take to lift that against the spring? Well, that's what determines nozzle opening pressure. You might set that spring tension by changing the number of shims, or maybe a screw that can adjust how much tension is on that spring. The nozzle opening pressure is what we're talking about here. Okay. As soon as the nozzle opens, the fuel pressure is now going to start leaving through some spray holes at the bottom of the injector. Okay. Those spray holes, where they are physically located, and whether they're clean or whether or not they're eroded to the point where they're bigger than what they were originally, that's going to determine your spray pattern and your atomization. Okay. Now, while you're busy pop testing an injector, what will happen is you're pumping fuel through that high pressure line and out those spray holes. But as you pump the fuel, as soon as the nozzle opens, the pressure from you actually pumping it into this passageway over here, it's going to drop. And as soon as that pressure drops, the spring closes the needle again. And then the pressure builds as you continue to push the handle down, it pops open. And this happens over and over really, really quickly. That's the chattering sound you hear when you're doing a nozzle test. Okay, so your fuel injector nozzle on that pop tester, it's going to open at a certain pressure, but if you continue to push that handle down, it will make that chattering sound. That's actually a good thing, because that tells you that the needle isn't stuck and hanging up inside of its bore. It's moving nice and freely. So chatter is an important thing. Okay. If I knew what the nozzle opening pressure was, and I was to raise the pressure in that fuel passage to maybe 500 psi below that nozzle opening pressure, I could look and see just how well we were sealing, right? I don't want it to leak out of there. I want it to stay shut when I'm not trying to inject fuel. So I can check and see how well it seals. I can also find out how much fuel is leaking past the bore inside of this injector and making its way out the return passage. Okay. So there's a couple of different tests that I can do, and we've kind of outlined them, but let's go ahead and make a list of them. The first test is nozzle opening pressure. Okay. The second test, like we said, is while we're busy pumping the handle on our nozzle tester, we're going to check and see what the spray pattern is. We want it to be uniform and how well the fuel is getting atomized. If those holes are all eroded or if they're plugged, that's going to affect the spray pattern and atomization. Okay. The other thing I'm going to be doing is I'm going to listen. I want to hear it chatter. Okay. That chatter test, that's telling me that that needle isn't hung up inside there. If it is hung up inside there, it's probably all gummed up and needs cleaning or replacing. Okay. I'm going to take and raise the nozzle, the pressure to the injector with the nozzle tester to about 500 psi or so below the nozzle opening pressure. And I'm going to check and see if I have any needle and seat leakage. And I'm also going to watch and see how much fuel is coming out the return side of the injector. And the needle and seat leakage, that'll tell me if the needle is worn out. Return leakage will tell me if the nozzle assembly itself is worn out internally. Okay. So this right here, this is hydromechanical fuel injector testing. These 5 steps here, or 5 things that you would do while you're busy checking or testing a nozzle, these are some things you're going to want to know. Guaranteed. Okay. Okay, so this is for hydromechanical. Yeah, hydromechanical injector nozzle testing, or just your standard nozzles that you would have with a mechanical fuel injection system.
So that would use like a separate fuel pump, like an inline or a radial.
Yep. Nowadays, do we still see fuel injectors like this? Yes, we do. Okay. Nowadays, they're probably being used with a electronic distributor type pump on smaller engines. That's where you'd still see these. Okay. Historically, this was the fuel injector, right? Nowadays, another place that you're going to see these is as part of an electronic unit injector. This is just the bottom part of the unit injector. It still has this nozzle part. It's just the bottom bit of it. So when we're talking about unit injectors, we have mechanical unit injectors or electronic unit injectors. Okay. The thing that makes those unit injectors is the fact that we're combining several different functions into one physical unit. We have the high pressure pumping element, we have the metering system, and then we have the injector nozzle itself. Okay. So if we're talking a mechanical unit injector, these ones here are typically going to be a port and helix type metering system where you have that plunger and barrel assembly inside the injector. You can see on this injector here, we have a rack that goes through this injector, and that's going to have the teeth on it that rotate the plunger inside of the barrel. And there's going to be a linkage that connects a mechanical governor to this rack. Okay, and that linkage is going to connect the mechanical governor to all of the injectors. So all the injectors, they move in unison when their racks move in and out. Okay. So what that means is we have a couple of things here that could be adjusted on this mechanical unit injector. You have the rack position. You want all of the racks holding all of the plungers in the same relative position. Okay, that's going to be your fuel metering You also have a rocker arm that connects the top of this injector to a cam lobe. Okay, so that rocker arm, it's going to have some means of adjustment, usually a bolt over here, and that bolt is going to set the position of the plunger relative to the cam. What I want is I want all of those plungers in the same relative position where they're supposed to be. If I was to adjust those plungers so that all of them were sitting a little bit lower, right? If they're all sitting a little bit lower, that would mean the port and helix metering system inside of this injector would actually be sitting closer to the port. And that would mean it would close it off and start injecting sooner. So setting the plunger lower on a mechanical unit injector advances the timing. Okay, so if you wanted to make a note on these, plunger height adjusts timing. Rack position adjusts fuel metering. Okay.
That bolt is tighter or further down, that advances your timing?
Yeah, because the plunger is sitting closer to the port in the barrel, it doesn't take as much movement for it to reach port closure and start injecting fuel. So if your plunger is lower, that advances timing. That would really depend on what type of engine you're talking about. This injector here is out of one of those old mechanical unit injector CAT engines, like your 3114s, 3116s, those type. Okay. Detroit used injectors like this. Lots of manufacturers, well, I shouldn't say lots. Some manufacturers used injectors like this in the early days of unit injector type systems. The only place you're ever going to see these nowadays, in North America anyways, would be old two-stroke Detroit engines or old CAT equipment that used those 3114, 3116 engines. And some of the early 3126 series engines would have had this type of fuel injection on them as well. Most of the 3126, which was the precursor to the C7, most of those were the first version of that Huey fuel injection system. Okay. As we get into electronics here in level 4, we're going to start talking about electronic fuel injection systems to a certain degree as well. But in the context of what you talked about in your level 3 stuff, mechanically, how did these things work? Well, these ones, they still operated kind of on like a fill pump and spill type strategy. Okay, an electronic unit injector, there's a plunger inside there and it moves up and down. Okay, that plunger, it's actually adjustable. There's an adjusting bolt that sets the initial plunger height on these. In terms of how we changed how much fuel got injected, we just had a solenoid that opened and closed a valve, a spill valve, right? So if I wanted to inject fuel, I would have to be moving the plunger, that would have to be happening, and I'd also have to close the valve that was letting fuel spill out, that would start building pressure inside the injector. And then that fuel pressure inside the injector, once it got to nozzle opening pressure, it would open up the nozzle on the tip of this injector. And here we have a cutaway of this. I think this one we're going to go ahead and throw in our notes. Over here. So over here, this is our electronic unit injector. This one has a hydromechanical nozzle on the bottom, like I was saying earlier. Okay. That hydromechanical nozzle, we can probably recognize as a spring. There's the nozzle, the needle and seat on the bottom. So this all works very much the same way as what we were looking at over there. We have a plunger built into this one, that we have a rocker arm and a camshaft. It's going to operate that rocker. We're going to have an adjusting bolt, right? That adjusting bolt is going to set the starting position of the plunger. Now, unlike a mechanical unit injector, the starting position of this plunger here doesn't directly affect the timer. Okay? It'll adjust your timing window, but it doesn't directly affect your timing. What does control the timing is when the solenoid number 2 is energized. When you energize that is going to set when we start building pressure, because we close off that leak path to the return. And how long we keep that solenoid energized for is going to control how much fuel actually ends up getting injected. So that's my fuel metering.
So that plunger adjusts when you control the travel?
I like to call it the timing window, right? We want that plunger to be able to pump fuel when the ECM expects it to be able to pump fuel. So if it's set too high, we might not have got port closure yet. That means we're going to have less available time that we could be pumping fuel. If it's set too low, we run the risk of running that plunger all the way down into the bottom of its bore and damaging the injector. Okay, so when you're setting your plunger height on a fuel injector like this, a lot of times it's going to be maybe just a simple little go, no-go gauge. Sometimes they'll ask you to have the plunger all the way down on the high side of the cam, and they'll have you seat the plunger and then back it off 1 or 2 flats on the adjusting nut. I've seen that as well. So obviously it's not that precise of an adjustment, but it does matter. Okay?